I'm Shahar Samral, a senior at Leland High School in San Jose, California. Today I'm going to share the self-driving car that I've built. I started working on this project back in April of this year. I've assembled the hardware for the car, but most of my efforts were focused on developing the software that actually drives the car. As a quick roadmap in this video, I'm going to introduce the car's hardware, then go on the software and algorithms of the car, followed by an actual demo. Okay, so first of all, here's the self-driving car itself. In the center here is the Raspberry Pi. The Raspberry Pi is actually a miniature computer based on the Broadcom SoC chip, which is an ARM quad-core processor clocked at 1.2 GHz. The chip itself also comes with inbuilt Wi-Fi, which is really cool because it makes it easy to transfer code over the air. It's a little hard to see, but this is the SD card, which acts as the hard drive of the car. It holds the Raspbian operating system and the code that I wrote. Over here is the USB ports, and here's the Ethernet port. So it's a little hard to see, but here are the GPIO pins. GPIO stands for General Purpose Input and Output. By connecting cables to these pins, we're actually able to control various components of the car through the Raspberry Pi, such as the DC motors and the blue servo motors. Over here on the front of the car is the camera module, connected via USB to the Raspberry Pi. The camera has a 120-degree wide-angle lens. It's actually facing down to look at the track and capture the lanes while it's driving. The resolution of the camera is actually 1080p, but unfortunately, I can only use the camera at 480 by 320 pixels, which is only 320p. This is because processing anything more than that actually brings down the performance drastically. It took me a while to find a perfect camera due to these issues, this is why this is the fourth camera I've tested. Alright, so here's the PWM driver chip, which is connected to the Raspberry Pi via the GPIO pins. PWM stands for pulse width modulation, and allows us to control the servos and the DC motors by controlling the duty cycle of the pulse. This allows us to move the motors and servos in one direction or the other. This PWM chip has 16 channels, allowing us to control up to 16 different devices. At the back of the car is where our two DC motors reside. These motors drive the back two wheels, allowing the car to go backward or forward. The motors are controlled by configuring this chip here. In addition to selecting which direction the motor should move, we need to control the speed of the motors too. Speed control is done through the PWM module I discussed earlier. This here is a step-down DC-DC converter module. Its job is to step down the 7+ volt supply from the batteries down to 5 volts that is needed for the Raspberry Pi. Here is the servo motor, which is used to steer the car left and right. This small motor is very precise and it allows us to make marginal adjustments when it comes to keeping the car in the lane. This servo motor is connected to the same PWM driver chip. So how do I make this all work? Well, the simple answer is that I use my laptop to connect to the Raspberry Pi over the Wi-Fi network, allowing me to add and modify code on the SD card. This is all done through VNC, or Virtual Network Computing. The software runs on my laptop and allows me to connect to the laptop, or connect my laptop to the Raspberry Pi and control it as a virtual desktop on my laptop. So let's log into the Raspberry Pi right now. So the VNC software uses the IP address to connect to the Raspberry Pi. Once I log in, I will be greeted by the Raspbian window interface. From here, I can go into the terminal, which allows me to develop code directly on the Raspberry Pi. All the code is saved on the SD card on the Pi itself. Okay, let's move on to software. As I mentioned before, the operating system, the code, and the drivers I developed, and all the libraries sit on the Raspberry Pi's SD card. I use the Python programming language to do all the coding. The clear advantage for me was the convenience factor. I could make quick changes to the code and see the effect without even compiling it. The same goes with debugging. The drawback is that it is slower. If I use C or C++ or Java, I would have way more headroom. The car has to process images of the track to find the lanes, and with high performance, you can process much more frames per second, which could lead to more reliable lane detection. This allows you to run the car at higher speeds. So here's the block diagram of the high-level software architecture of the self-driving car. The entirety of the program is written following object-oriented methodology. Vast majority of the code is contained in one class called SDCar, which stands for self-driving car. This method uses the device drivers and support methods to do its job. This method is called repetitively to run the car. So let's go over what actually is done in this loop. The first step is to capture a frame or image of the track in front of the car using the camera. This color image is then converted to grayscale with a resolution of 480 by 320. Following that, the frame is analyzed to detect edges, which are analyzed to detect lines. These functions are performed using OpenCV library. Following that, my algorithm kicks in to detect lanes to drive and steer the car. Developing and perfecting this algorithm is where most of my time went into this project. Okay, let's go on to the algorithm. The algorithm has three main parts. First part is the lane detection. The challenge here is to extract lanes accurately out of the frame that contains all kinds of lines in all directions. For example, shadows of objects around the track and glare all show up in the frame as lines. My main job here is to filter out all that noise, meaning anything that is not a lane. So, I can zero in on the true lanes. This filtering process uses multiple filters. The output of these steps of algorithms are two lines that are supposed to be the lanes. The second part of the algorithm is the turn vector generation. This phase starts with one or two lanes detected by the first phase. From these lanes, it generates a turn vector, which is a vector line that originates from the middle bottom of the frame and points to the direction that the algorithm believes the lanes are going in. Frame by frame, this turn vector is adjusted based on how the track in front of the car looks like and direction it is leading to. The third part of the algorithm is steering control. One of the challenges here is to effectively deal with the instantaneous noise in the turn vector. A perfect shadow or a glare in the frame can look like real lanes from time to time, and the algorithm can be fooled. To reduce the mistakes, the algorithm uses thresholding, which makes sure that once in a while, wild changes in the turn vector don't take the car into the woods. The second challenge is that it is possible to detect only one lane in a frame, because the car drove too close to one lane and the other lane dropped out. To prevent these problems in such situations, the algorithm maintains state and remembers how the lanes used to look like in the immediate past to use that as the guidance. So this loop that acquires the frame, processes it, detects lanes, and then steers the car. This is performed as fast as possible. The faster this loop is run, the higher the frames processed per second, and the higher the speed at which the car can respond to the changes in the track, and therefore, faster the car can run. Currently, the Raspberry Pi can process 15 frames per second. So, now it's time for the demo. Alright, let's start the demo. Here's the track. The first phase of the project was developed on a straight stretch of track. The second phase was actually developed on an all-circular track. For this demo, I've chosen an oval track, which has both straight and circular stretches of the track. It's a little under 9 feet by 5 feet, which is the biggest size I can fit in this room. I'm going to put the car down on the track and initiate the execution of the program on my car from my laptop. The car will start running and will continue to run until I stop it. Okay, we started the car on the straight part of the track. Now let's start it from the circular part of the track and see how it performs. Okay, now that you've seen the car go on the track, I want to give you a feel of how the car and the algorithm actually sees the track, and how it's making a sense of everything that it sees. Alright, so I've put the car on the straight part of the track, and as you can see on my laptop window, you're seeing a live view of what exactly the software is seeing and generating. This window is sort of like an eye view into the software. Even though the car is not running, it's actually capturing the frames of the track and processing them. The black lines in the video are the actual lanes of the track. You can see the tiny ragged red lines. These are the lines that are detected by OpenCV. These lines are actually fed into my algorithm. The two green lines are actually the lanes detected by the algorithm. And that's where the algorithm actually thinks the lanes are. Now the blue line in the middle, that's the turn vector. Based on where the green lines are detected, the turn vector will point in the direction that the car should be steered in. You can probably hear the car's steering servo make a little bit of a noise. My algorithm is actually continuously trying to make little steering adjustments while standing still. Okay, I'm going to turn the car to the left. Watch how the camera feed of the track lane changes, and how the software reacts and produces those detected lanes. The turn vector you'll see will actually change as well. Alright, now I'm going to turn the car to the right. Again, pay attention how the software reacts. Alright, let's move the car to the curved portion of the track and see how the car gets ready to take off from the curved section. Again, pay attention to the laptop screen. As you can see, the green lanes on the sides are being detected at an angle, because that's how the track is. The turn vector is also pointing at an angle, indicating the direction of the steering because of those green lines. If you look at the wheels of the car, you can see that they're being turned in the direction of the track. So that means the car is ready to go in the correct direction. Okay, I hope you guys enjoyed the demo, and thank you for watching.